So this is from the homework number 43. When I see this, my instinct is to do the following. So this is log of, let me make sure I got this right, log of x to the log x equals 4. My instinct is to just start undoing stuff. Because it's kind of like the way I think about this is, well, if I had the square root of x equals 64, I would say, or what's one that works? 16, or oh no, it's the other way around. But I'm sorry. If that equals 2, I would say, okay, well, we square both sides to undo the squared. The square root, and so now we have this equals 4, and then I'd square again, right? And so that's my instinct, is to do the same kind of thing here, is to say, well, undo the outermost thing. And so let's just see what happens when I do that. And pay attention to the reasoning I'm about to talk through right here, because this is going to come up later with other problems we're going to talk about. Is like, what's the same kind of thing I've been doing before with anytime I solve an equation, I try to find the innermost thing. This looks like the innermost thing. Oh boy, that's ugly. Because I know I'm trying to solve for x, and I ask myself, where's x? Well, is the innermost part of it, right? But there's also that. So that's going to screw us up. And we're going to see how that's going to screw us up here in just a minute. But my reasoning is, okay, well then, all right, there's kind of something funky going on here, but the outermost thing, in other words, the last thing you do, you put on your socks, then you put on your shoes. So to take off these shoes right here, I'm going to undo log base 10. The way I undo log base 10 is I take both sides, raise it to the 10. Okay, so then that gives me x to the log x of, I guess, 10 to the 4. I'll just write it as 10 to the 4. Oh no. And now it's like, well, now what? And you could go back and forth all day, and you say, well, let's take a log of both sides, because the thing I want's in the exponent. I'm going to take a log. That's just going to take me back to where I came from. Uh-oh. And so at this point, when I get to here, and I'm starting to go, wait a second, maybe there's a better way of dealing with this. And what I notice is, so starting from the very beginning, is one of the main reasons we take a log of anything is to make the exponent drop down, because we have that nifty property of logs, that log of any base, any number raised to any power, right? We think about it as exponents drop down. And that's one of the reasons that we take a log in the first place. But this is like that work is already done for us. We already have log of something raised to a power. And so I could go ahead and apply this. And that's so my instinct to just brute force undo all the stuff kind of led me to something I don't really know how to deal with. So I'm going to look at it a different way. And one of the things I want to be thinking about are, what are all the properties of logs that I know of? One of them was that, our favorite one, that whatever's in the exponent drops down. And when that happens, we get log x times log x equals 4. Put differently, you have some number times itself equals 4. So, oh, there it is. That's the same thing as log x squared equals 4. And from there, you should be able to plug along with 43, because you've had similar ones in this very homework that are very similar to that. And so now, look at the difference, right? On one hand, if you're trying to find the innermost thing, x, it's like, well, x shows up in different places. Yikes. But here now the innermost thing is x. X gets logged, right? You take the log of x, then you take whatever that is and do squared. And so we'll want to undo the outermost thing, and then we'll just work our way into undoing it until we get to the innermost thing, which is x. So we good with 43? I can't hear you.
Yeah.
Okay, cool. So that one's difficult. I didn't really even notice how that guy. So, okay, as for the rest of these, I think there's 43, because you did 41, which was, as far as I'm concerned, the hardest one on the page. And then we just have stuff like this. Okay, so this is what I wanted to talk about with the rest of these. So let's say I had this equation right here. And I told you to solve for x. What is the first thing you would do?
Divide by 3.
Okay, and we would end up with 5/3 equals x squared. And then you would do what?
Take the square root of both sides.
Root of both sides. And so we'd end up with a plus or minus 5/3 equals x, right? Now, the way, I know I've said this 1,000 times and it probably just goes in one ear and out the other at this point, but the way that I think about the phrase solve for x is get x by itself. And that's what you were doing here, right? You whether you know it or not, you looked at that and said, is x by itself? And you said, no. And so you said, well, I need it. You didn't even need to think about it. You said, I need to get rid of that 3 right there. Right. And you're right. Like that's kind of what, and the way that I've suggested doing it is what I was just saying, is you look at the innermost thing, the thing that you're looking for, and work your way out. And so we could think about this as what happens to x. That's the thing I want to get by itself. So first he gets squared, then he gets multiplied by 3, and so we get rid of the 3 and then get rid of the squared. Okay. And okay, so do one more example that's like this. It should be suggestive. Now, let's say I had this equation and I said solve for c. What's the first thing that you would do?
Divide by b.
Right, because you're thinking I need to get c by itself. And so you say, okay, that's one step closer to getting c all by itself. And then what do you do to finally get c by itself?
Take the square root of both sides.
Square root of both sides, and that gives you a plus or minus a over b equals c. And that's how you get c by itself. Okay, so let's change this up just a little bit. Let's make this slightly different, almost slightly different. Now, and you notice I used a, b, and c because I didn't want us to get in the habit of thinking x is the thing we're always solving for. It could be any letter. You could have just a bunch of big jumble of letters like we're about to have, and I could tell you to solve for any one of them. Like if I said, for instance, solve for b, you would have said, well, I need to get b by itself. B gets multiplied by c, and so by c squared, and so I get it by itself by doing that, right? And so that's the idea there. It's still the same game, basically. Like, how do I get this letter by itself? So let's change this slightly. I'm going to replace that squared with a d. And I'm going to say, let's solve for d. What's the first thing you want to do to get that d by itself?
Divide by b.
Divide by what?
B.
B is in Bravo. Yes, yes, exactly, right? And it's the same kind of idea. And this is, it starts to get a little funky because there are a few different ways we could go about doing it. Like, I mean, we could have taken this right here if we wanted to, and we could have said, take the square root of both sides. So you go, okay, you take the square root of both sides, it gives me root 5 equals, and then, well, I guess 1x gets pulled out of there because I could simplify that. And then finally I get my root 5 over root 3 equals x. which is the same thing as I got using the other method. So there are a few different ways we could do it. But to me, when I look at something like this, I think get D by itself. And so again, I'm looking at it as D is the innermost thing, and I'm just going to kind of follow it out. It's like, what happens to D? Well, the first thing is, I guess D gets plugged into the function c to the x. So you can think about that as we take D and plug it into an exponential function. So that's the first thing that happens. Then he gets multiplied by B. And so just like you said, my first step is going to be to undo the last thing, is divide by B as a Bravo. Okay. And so now, how do we go about undoing this bad boy?
Okay. You do the log. So you do log base C.
No. Yes, you're right. That is what you do. But I am saying, and I said it explicitly with number 49, and I had just completely overlooked 47 because it says to use special logs. Like in this case, it would have said use log C. You're never going to use log C because you're going to get an answer, and then your boss is going to go, okay, and what's the value? And you're going to go, I don't have a log C key. So how did you, in your homework, you had a question like this. And you were to solve for X. What did you do to both sides?
I took the natural log of
The natural log of both sides. And I'm going to go ahead and recommend, no matter what the book says, when you're solving an equation, use the natural log. Unless, and this is one of the few cases, like if you happen to have like 10 to the x equals 100 or something like that, then yeah, you might want to take log base 10 because that was just going to make your life easier. But in the real world, we don't have log base C anything. And so, yes, you're right. You could take log base C, and that is exactly what would undo that, because you have C to the D. And like in a few times, you don't need to bother writing this down. You're absolutely right that if you took log base C of C to the D, you would get your D back. And that's how we usually think. How do you undo C to a power? Well, you log base C of it, and that's how you get it back. But this whole section, we are trying to think practically, how would we compute this? And so we're going to do that with natural logs. And so natural log of A over B, natural log of C to the D. And now what do we do? What's the thing we're trying to get by itself?
D.
Say, well, I didn't hear you.
Are we trying to get D by itself?
D is in delta, yeah. And so how do we do that? What's our favorite property of logarithms? The most useful property of logarithms?
Oh, you can take the D out and put it in front, right?
Exactly. That is what is so useful. That's why I'm calling it the most useful and our favorite property of logarithms, because up until this point right here with what I've written, that D has been locked up here in the exponent. And it's like, how do you get it by itself? Well, yikes. Well, we start by isolating the exponential thing, the C to the D. And then it's like, well, how do I get that d to drop down? If only I could get him out of the exponent. This is how you do it. You take a log, because that is our most important, our favorite property, the most useful property of logarithms is that it pulls things out of the exponent. Now that it's out of the exponent, this just means d times some number. And so how do I get the d by itself finally?
Divide by natural log of c.
There you go. And so now the d is all by itself. And on the left-hand side, I have natural log of a over b all over natural log of c. Now, your book said to use the natural or use the log base c. And so when you look in the back of your book, it's not going to look like this at all. Another thing, though, even if it did say to take the log, the natural log, in order to do this, they might have done this. Now, just watch. Don't bother writing any of this down because I don't recommend doing it this way. They very well may have, and in one of their examples, they in fact do something like this. They start here. And in order to solve for c, they start by taking the log of both sides. And then they say, well, we're trying to get d by itself, but you can't just pull that out because the entire thing is not to that power. And so then they use a different property of logs. They use this first. They say, well, this is the same thing as log of b times that stuff. And so we know that that means this right here. This is how they split that up. And then they say, okay, we're trying to isolate this guy. Now you saw what I did there, right? That's some number times some other number. And then they split it up into the logs like that. And so then they say, okay, now we need to isolate this guy. And so I'm going to subtract this from both sides here. Oops, c to the d. C to the d, like that. And then they do what we did, which is natural log of a minus natural log of b equals d to the natural log of c. And then finally, they divide just like we did to get this. Natural log of a minus natural log of b all over the natural log of c. And so it's possible that in the back of your book, they have this answer and you go, oh no, I got the wrong answer, until you remember, oh yeah, there's that property of logs. In fact, we used it earlier, right? That something times something breaks up as a plus, but something minus something is how you break up a division. And indeed, you know, we talked about this before, right? When we were first talking about properties of logs, is that log of a minus log of b is the same thing as log of a over b. And so you know, and like I was showing you earlier, right? Like the very first example, 5 equals 3x squared. We could have taken the square root of both sides to start with. And as long as we're consistent, we will end up at the same place. And so that's kind of what's going on here as well. The last thing to talk about. So any questions with this before we move on?
No.
The last thing to talk about, which should help you with the homework, which I'm going to say just the stuff that you didn't do, it was like 1, 2, 3, 4 problems maybe, that just turn them in with the homework that's tonight. So turn them in on Monday with your other stuff. The only other thing that's really going on is a similar type of equation to this, only instead of a equals b, c to one variable, it's like 2 variables up here. And so it's like k d, and they say solve for d. I'm sorry. I'll make that better. They give you something like this, and they say solve for d. And nothing's different here. Just like in your mind, you can kind of just imagine, oh, well, wait a minute. Or, well, actually, let's do this methodically. It's like, okay, hold up. I'm trying to get d by itself. So what happens to d? Well, the first thing that happens to d that I could see is he gets multiplied by k. Then he gets thrown into an exponential function. Then he gets multiplied by a number, and that's the last thing that happens. So I'm going to undo multiply and get that, and we would have this. Then I'm going to log both sides because the thing I'm looking for is in the exponent. So I take the log of both sides. But now the only difference is k and d come down together, and I have k times d right there. And so finally, I'm left with a kd right there. And again, d times some number. I guess the last thing we would want to do is divide by that number to give me natural log of a over b. And I'll just put a k down into the denominator like that. And so let's a quick think about this. I said the first thing that happens to d is he gets multiplied by k. Then he gets exponentiated, I guess. Then he gets multiplied. And so the last thing was multiply, so we divide and do that. Then there was the exponentiation, so we undo the exponentiation with a log. That's the second thing we do, right? Then then of course we got to take him over and blah, 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 blah. But then the last thing that we do is divide by k. And so multiplication, exponentiation, multiplication, we undo that with division, log, division. And so there we go. Any questions?
Yeah.
Yeah.
For 47, it says for t, use log b.
Use the natural log. Like I said, I missed that. Well, you can, and it's right, you do. But like I'm saying, we don't want to get in that habit. Like that's never.
So can you like say that problem out loud and translate it for me? Because I thought it meant, for some reason, I thought it meant like substitute log b for t.
Oh, so what it's doing, okay, so what it's doing is basically like this. It's the same thing as this. Like, if they had given you this, they would have told you use log C. What they're getting at is they know that somewhere in all of the calculations that you're going to do, you're going to have to take a log. And in that one, they're telling you use log C when you take a log. I'm saying don't use log C because you're never going to use log C. Use the natural. So there will come a time when you're trying to get D by itself that you will want to take a log, or you will have to take a log. Which type of log should you take? Log base 2, log base 10. It's telling you use log base C. And I'm saying that's never going to help you in the real world. So let's not get in that habit. Instead, use natural log. Does that make sense? So in the case of 47, and I'll just make it explicit, but we're not going to go through the calculation. They're saying y equals k b to the at, and they say use log b. They're saying that because they know that you're going to start peeling stuff away in order to get t by itself. Solve for t again. So they know that you're going to go, okay, t needs to get by itself. What happens to t? That and that and that. Okay, so I'm going to start peeling things off in order to get t by itself. And then they know that at some point you're going to have to take a log. And they're telling you explicitly that when you do that, use log b, which would be nice and clean and make everything nice and neat, but it will never help you in the real world when you actually have to go calculate this. So I'm saying let's get in the habit of using natural log instead. I'm going to say use natural log for when you have to take, when you finally need to drop that stuff in the exponent out.
Okay.
Is that clear?
Yeah.
Good, awesome. And so that's that. Log A solve for Y. Yeah, you should have enough to go with that. So, okay, a couple more things from this chapter that we need to go over that I think is pretty good. It's the Richter scale, the decibel scale, decibel measure, and pH. And then we're going to get into our main topic of today, which is interest. That's my book. Yeah, and it's open, and I would appreciate it if you kept it open. So the Richter scale is defined as the log base 10. Oh, yeah. This is weird. The intensity of, so we're talking about the Richter scale. I'm assuming that you've heard this before. We're talking about an earthquake, right? And there's a measure of how intense that earthquake is. And the thing is that in the world, earthquakes, the intensity of earthquakes scales by a lot. Like one earthquake might have the power of, say, 1,000. I'm just throwing this out there. 1,000 joules. A joule is a measure of energy. So, just so you know, Newton meters. You okay? So, like, yeah. So a joule is a measure of energy, and so one earthquake may have 1,000 joules of energy that's released, but another earthquake might have like 10 million joules of energy that's released. And so it's like, if we just talked about it in terms of, say, energy, be like, you know, then you're listening to the news and you hear an earthquake off the coast of whatever had 10 billion 500, you know, 10 billion whatever, and it's like scale is off. And so what we do is we try to scale it down because by basically just talking about the powers of 10. And so when you hear something was like, there was an earthquake of magnitude 3 on the Richter scale, what that means is that the number that was in here would have had to have been 10 to the 3. If they say there was a magnitude 8 earthquake, then what they're talking about is that the intensity of that earthquake was on the order of 10 to the 8. Now, this thing, right, that means that the intensity is on the order of 1,000, right, 10 to the 3rd. This thing is on the order of 1 with 8 zeros behind it, way bigger, right? And so, because in the real world, there's such a great variability of how intense an earthquake can be, they're like, let's just shrink this thing down and just talk about the log of it. And so that's where it comes from. And so I asked Mika this morning, who has a PhD in seismology. I asked her, so what's the intensity of? And she goes, oh God, I don't know, look it up. Like, it's so, and I'm like, well, how do you not know this? And she's like, well, the thing is, in Washington, we don't use the Richter scale. We use, oh, she told me, I forget what it's called. They use something else. The Richter scale is calibrated for California. And so, interesting fun fact right there. But basically what this is the intensity is defined as the amplitude of the waves. And so here I'm kind of thinking about time here, right? So if like the earth is moving up and down like this, right? And as time goes on, if you kind of start moving along, a seismogram looks like this. And what we're talking about, the intensity is the amplitude of that wave right there. How big it is from the center. You could define it as the amplitude like totally that way, but the way we define amplitude is from the center, how high does it get? How low does it get? That right there. And so that is actually the intensity. Now, this is the weird thing, and this is why I'm going into this, is this, what the heck is this? And they could just gloss over it in the book and say, you know, relative to some, how do they put it? Where I sub 0 is the minimum. Oh, no, I'm sorry. That's a different thing. I times 0 is the, I don't even say it. It must show up earlier in the thing. Oh, is a minimum intensity used for comparison. What that means is, what it actually is it's there's a minimum intensity, a certain distance away from the station it has to do with how far away the detecting station is from the epicenter of the earthquake. So the thing is earthquake in here, and you have your station over here. It has something to do with the actual distance there, and there's a way of there's an agreed upon minimum intensity, and it's called I sub 0. But in the homework, they're going to ask you to compute stuff like this, and I'm just going to show you how to do it. And so let's just kind of think about what this is. This is a measure of intensity, but it's compared to something. So it's kind of like saying, how many times bigger is the intensity of this earthquake compared to some background level? And so for instance, it says the Los Angeles earthquake. This is number 32. And we're going to get kicked off in 5 minutes, but and I looked it up. Apparently Zoom no longer is Zoom, unless you're paying for it, is kicking everybody off at 40 minutes now, no matter how many people are on. So number 32 says the Los Angeles earthquake had an intensity 5 times 10 to the 6 times I0, which I'm going to think about as the background or the comparison value. And they say, what's this on the Richter scale? That's the question. Well, it's very much, we're just going to plug this in. And so it's saying that the intensity here, the experienced intensity is 5 times 10 to the 6 times whatever that background is. And so I'm just going to take that and plug it right into here. And it says R is equal to log of 5 times 10 to the 6 times I0 divided by I0. Oh, that's convenient. And all of these questions that you have are going to be like this. It tells you how much times the background thing is, or the reference thing, so that these guys cancel out. And now you're just computing the log of 5 times 10 to the 6. Right now on a calculator. So the way that we do this, there are a few different ways of doing scientific notation on a scientific calculator. I am trying to compute log of 5 times 10 to the 6th. I could, if I were so inclined, just go 5 times 1, 0 raised to the power of 6. Did you see how I did that?
Yeah.
Whoops. Uh-oh. So now I need to go forward and then in the parentheses. And it gives me this value right here. So that would be a 6.7 on the Richter scale. Another way of doing it is to use, can you see this right here, that double E? That double E means times 10 to the. So for instance, we go log 5, and then this is how I say this in my head. So it's blue. So that means I need to hit the blue second key. And now when I hit this key where I see the 2 E's, it gives me that little E, which means times 10 to the, and then I put 6. End parentheses. That means the same thing. That's how you use scientific notation on a scientific calculator. And then you do it and you get the same thing. So, yeah, buddy, it's open. It needs to stay open. Please leave it alone. So, okay, that is what we are trying to do here. And so we got 6.7 on the Richter scale. That's all there is to that. You're also going to have questions about the decibel scale. It's the exact same thing. It's almost exactly the same thing. The only difference, and can I get rid of this stuff down here?
Yeah.
Yeah. You did it. The decibel scale is a measure of sound intensity. And it's almost exactly the same. We're going to call it L for loudness. And its loudness is this, but then you just take it and multiply it by 10. I think that has something to do with deci, the decibel schedule. There's deci is 10, right, in Latin or something like that. And so that's that. And it's the same kind of question. They give you stuff. Peter, please stop. I need to use this right now. I have to see this. So for instance, they'll say, find the loudness of the threshold, blah, 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 where the intensity is 10 to the 14 times that right there. And so you just say, oh, it's 10. I is 10 to the 14 times I0. And so then you say, okay, the decibel intensity, or the decibel, it says find the loudness. Find the loudness in decibels. So you go 10 to the 14 times I0, divided by I0. Those cancel. And so actually we could just do this one. We don't need anything because it happens to be log base 10. Log base 10, 10 to the 14, that's just 14. That's just 10 times 14 right there, right? Log base 10, 10 to the 14. 10 times 14 is 140. And so that would be that. That was number 30. I'm going to get kicked off any second now. That makes sense? I went through that fast and furious, but that's the idea behind that.
I think so.
Okay. That 10 on the outside is just part of the definition, and he just came along for the ride here. And then finally, I said, well, that just reduces to 14. If it doesn't reduce nice and easy, use a calculator. That's what it's asking for. And that's how we do it. So that's those types of questions. They're all pretty much exactly the same. The other type of question that you'll have is basically the reverse of this, which is like number 34. It says that an earthquake has magnitude 5 on Richter scale. And it'll say, what is its intensity? What's its intensity? And so I'm just going to think about this. I'm not going to use my brain at first. I'm just going to say, okay, hold up. I know that the magnitude on the Richter scale, I'm just going to write down the formula. It says it's the intensity divided by that intensity there. They didn't get everything before, right? They told you that it's something compared to this value I0, the background or whatever, the comparative value. They haven't given you the comparative value. So what they're looking for then is the following. So right now, I'm just going to say, okay, hold up. Magnitude 5 on the Richter scale. That means that the output of this is a 5. And so, okay, 5 is the output, log I over I0, not using my brain yet. And I'm going to say, okay, this is my given thing. I'm trying to get I by itself. I gets divided by something, and then it gets a log taken. I'm going to undo that by, I guess, exponentiating both sides. This is log base 10. So I'm going to take 10 to both sides, whatever, log I over I0. The whole reason I did that was to undo this and make this come back out. And so 10 log 10 makes that go away, and I get I over I0 equals 10 to the 5. And now actually what we end up getting, again, it's asking what's the intensity. The intensity gets divided by some measure. And so we multiply to get rid of it. And it's going to be right here that the intensity is 10 to the 5 times bigger than that. You'll notice this was the other piece of information that they gave you in all of those previous questions. They told you that it's something is 10 to the 5 times more intense than the background or to the reference value. So this is that is the thing that you should end up with. So how you do those guys right there. Any questions on this?
No.
Was that a no or a yes?
Yeah, no.
Yeah, no. Okay. The last type of thing that we use logs for is the pH scale. And again, we use logs here because the variability of this, what is that? Well, that's this right here is the concentration of H+ ions in a solution. We're talking about the acidity of something. And I think it's the Bronsted-Lowry theory of acidity is that we can think about acidity as how many hydrogen ions are in a solution. And so there you go. And it's in something called moles per liter. And if we were taking chemistry, we would be going way into this, but we're not right now. So we're just going to say this is a certain measure of how many H+ ions, that is hydrogen ions, are floating around in your beaker or whatever, or in your milk or in your anything, any kind of liquid. This actually makes sense. So Peter, please stop. Please stop. And I think it has to be aqueous for this to work. But anyway, who cares? So this is another way that this varies so much. Again, it's like you could report this as saying, well, you have, 1 times 10 to the negative 14 of these things in there. But it's like, well, that's kind of hard to wrap my brain around. Let's condense that because it varies by so much. I'd rather, instead of saying 100 billion, just tell me like 8 or something, right? And so that's the idea behind this. Like, it is much easier to say what something is when the variability is so big. Just tell me the powers of 10. And this happens to be negative log. And let's see why that's the case. Why would they define it as the negative log? Well, let's see. It's number 36. So number 36 says that the concentration of H+ in a tomato that's all I guess we could think about if you were to take the juice of a tomato, right? And we measure the concentration of hydrogen ions in the tomato. It says that this is 6.3 times 10 to the negative 5. It says find pH. Okay, well, pH is defined to be negative log of that concentration. That's all it means. We just take the concentration of those ions, plug it in. 6.3 times 10 to the negative 5. I'm going to do this one step at a time. I'm going to actually pull up my calculator and compute log of that stuff right there. So here we go. Log base 10 of 6.3 times 10 to the, so I use the E key, -5, negative sign 5. And that gives me, oh, a negative number. Okay. Now, just to be clear, if you're not comfortable with that E key, let me show you what this would look like if you didn't want to use the E key. I'm going to say log base 10, 6.3 times 10 raised to the -5. And notice I did not use negative, like the actual white negative key over here in between the times and the plus. I used this negative key down here. I hit the right arrow to get me out of the exponent, and now I'm going to hit close parentheses. And I get -4.2, and we're just going to leave it at 4.2 when we go back to the board here, -4.2. So I'm going to stop sharing now. Okay. And so it says it's negative of this number that we got, which was -4.2. And I'm not going to worry about all those zeros. And so negative is a positive. Just think about what a log looks like real quick. Log comes up like this. This is log of any base that is bigger than 1, but in particular log base 10 of x looks like this. It goes through here at 1. Plug in a 10, you get out a 1. So anything that's between, any input to a log that is between 0 and 1, which this is, right? 6.3 times 10 to the -5 is this guy right there. That number, 0.4063, is like here. And so the number that we get out when I plug that into log is a negative number. It's -4.2. But this is a scale. We're trying to report some value. I guess chemists at some point were like, why are we going to work with negative? Like we want to condense this because these exponents vary by a lot. So we'd like to take a log. But if we just take a log, we're going to be dealing with a bunch of negative numbers. Let's just make it negative. And so that's what this is. They're just saying, just whatever you get out of it, just make it negative. And so it's negative. Or it's so that the pH value comes out to be a positive number. Sound good?
Yes.
Okay, so that's pH. And that's what that's going to be. Okay, so now let's talk about interest. I'm going to start simple. Start with a real simple question here. Let's say I had $100. And let's say I invest that for 1 year at a 10% interest rate. So in other words, the bank says, you give me your $100 for 1 year. I'll hold on to it for 1 year. And then I'll give you an extra 10%. At the end of that year, how much money would I have?
Close it, open. Look, way back. Eat it. Nice back. Nice back.
Please leave it alone.
Hi.
Please just leave it alone.
Yummy.
$100. And you're going to get 10% interest back from that. What's the total amount that you're going to get? break this down. What's 10% of 100?
10.
10. So you're going to get your original 100 back, and then you're going to get an additional 10% of that, right? So we should have a total of what?
110.
Oh, okay. So, okay. That was probably the worst way that we could have thought about that, right? Like just thinking of like without actually calculating this. And let's just see what we did though, right? We said, okay, I'm giving the bank $100. I know I'm gonna get my $100 back. And so let's call this, I don't want to call it P, but we're gonna call it P because the book calls it P. P, I think for principal, right? Because it's like you invest some amount, you get, I think it's called the principal, and then finally what you get back is like your return, but for some reason I think they just call it P, whatever. Let's think. We gave the bank $100, so we're gonna get our $100 back. We're at least getting $100. And then we got an additional, whatever the interest was, right? Which is some percent of the original investment. And what did we have to do? I asked you, what's 10% of 100? And you told me what?
10.
10. And how could we calculate that? How could we write 10% of 100 in math?
Could you write it as a fraction?
Well, in a sense, yeah, but usually with percentages, we like to use decimals. So how do I, just this problem aside, if I said, what's 10% of 5? What would you do? You take 5 and multiply by what to find 10% of it? What about 50%?
What's 50% of 5?
Mm-hmm. Okay, what's 50% of 10? Just what is half of 10?
5.
Okay, so we took 10 and multiplied by what to find 50%?
I literally don't know. I've never been good at percent. So.
So the way that we take a percentage of a number is we multiply by a decimal. And if it's 50%, we basically say it's, well, 50% means per 100. So 50% means per 100. 50 per 100 is Latin for 50 divided by 100, which reduces, and we usually write it as a decimal, 5/10, which is 0.5. Another way, the quick and fast way of calculating this is if you say 50%, another way of dividing by 100 would be to move the decimal point 2 places to the left. It has the same effect. Dividing by 100 has the same effect as moving the decimal places 2 points to the left, 2 points to the left. And so if I want to take 50% of a number, one way I could think about that is, well, when I hear the word 50%, I know it's half, right? And so, yes, of course, if you say, what's 50% of 80? I would say, well, half of 80 is 40, right? And so in that sense, I'd say 50% of 80 is, I would just say, well, take half of it, right? And what I'm doing there is, well, yeah, you just divide by 2, right? And that's great when your percentages are, say, 50, because it's easy to take half of something, usually. But that's not going to help us when we actually have to go calculate something. And so what we're going to do is say, well, another way of thinking about this is like 80 times a half. But since we're talking about percentages, it's much easier to use decimals because there's that direct connection there where you could say, wait a second, 50% of something means to multiply that thing by, well, 1/2, or you could think about it as move the decimal place over twice. You have a 0.5. That's the number that you need to multiply by your amount in order to get the percentage of that. So let's now the same way here. Can I get rid of this stuff right here?
Yeah.
So if I say 50% of 80, yeah, obviously it's 40 because that means 1/2. But if I had something like this with 50% of 17.3, well, I could think about it as 17.3 divided by 2, or I could just say, well, 50% of a number means to take that number and multiply it by 0.5. And that's way easier. I don't need to use my brain here. And it's not one that lends itself to like half of 80 is 40. That one was easy. This one, I could, well, I don't need to use my brain. I could just plug it into a calculator, but that's what it is. That would be half. Multiplying by 0.5 is the same thing as dividing by 2. So I just take my number, multiply it by 0.5, and now I have that percentage of that. So we'll do one more before we kind of connect this to what I was originally saying. So let me check your understanding here. How would I find 37%? 37% means what in terms of decimals?
0.37.
There we go. That's all you do. Peter, no. Close it, close it, close it. Thank you. Lock it, please. Lock it, lock it, lock it. Thank you, buddy. And so that's a great, and again, right, this just comes from the definition of percent means, well, you have 37 per 100. So that's a fraction. And we could just say, oh yeah, that means move the decimal place 2 places to the left and you get 0.37. And then if you want to know what is 37% of something. So if I say, what is 37% of 15, what calculation do I need to do?
Would you multiply 0.37 times 15?
We go 15 times whatever that percentage is. Again, right? That's what you're doing right here. Like this means the same thing as that. Just the same way that like 0.5 means 1/2. And so when we wanted to find 50% of 80, I multiplied it by 0.5. But 0.5 is exactly 1/2. So in a sense, to take 50% of something is to divide by 2. To take 37% of something is to, well, yeah, it's kind of ugly, but you see the idea is there's a fraction. This is a fraction, and you're finding that fraction of some number. And so if I wanted to, I could plug that into my calculator. I'm going to do it real quick. 15 times 0.37 7 turns out to be, that's nice, 5.55. And so we'd say, yeah, 37% of 15 is 5.55, like that. So let's tie this together right here. If I said 10%, what is 10% in decimal speak?
0.1.
0.1. So if I said, what is 10% of 741? What calculation do I need to compute?
Multiply 741 by 0.1.
There you go. Which happens to be the same thing as divide it by 10. Right? Because 0.1 is equal to 1 over 10. And so, and I'm using, I started this with 100 and I wanted to take 10% because it's easy to actually get numbers. But I could have said, what is 10% of 741? And well, 10% is actually easy because you just move the decimal place over one place. It's kind of how the decimal system works, tens. And so we could do that. We could plug it into a calculator, and I'm 100% sure that we would absolutely get 74.1, right? And so finally, we started off with $100, and the bank said, if you give that to me for 1 year, I will give you 10% back on top of that. So we want to know how much will the bank give us. We say, what is 10% of 100? And that one's easy to calculate because it's tens and 100s, but we don't want to make this easy. We want to see what calculation do we do to find 10% of 100.
100 divided by 10, or 100 times 0.1.
Times 0.1. And you're right, it is divided by 10. But since we're talking about percentages, we want to try to, we're taking a very easy problem, but we're anticipating that, hey, this isn't always going to be 110%. And so when it's like, find 37%, divide by what? Whoa. It's way easier to say, just take your number, whatever it happens to be, and we'll multiply by 0.37. So that's what I'm anticipating here. So I'm trying to keep, you're right, we could divide by 10, but it will be to our benefit to say, just take the percentage, multiply it by the number. So finally, this is what we're going to do. The bank is going to give us, let's find out. Well, we're going to get our 100 back. We'll get our $100 back, but on top of that, they're going to also give us plus 10% of that number, which is, you just told me 100 times 0.10, right there. And indeed, yes, I could calculate that if I wanted to and say, okay, well, that's 100 plus 0.1 times 100 is 10. We will get back a total of, and you already told me this at the beginning, $110. And that's what that is. Okay. Now, this is what banks do. They say, but if you let me have it for 2 years, I'll do that calculation again. We're gonna, in other words, we're gonna calculate this interest once a year. And so you give it to me for 1 year, and then at the end of that year, I'll give you that 10%. But guess what? Now you have $110 in your bank account. If you hold on to that in there for another year, I'll give you another 10% of that. Not 10% of your original thing. 10% of this. It's as though now they're saying, you know what? Pretend that we just gave you $110. Now you're going to take that and give that back to us. How much money would we have after 2 years? So this is, I'm going to put a little 1 right here to say this is the amount we would have after 1 year. That would be the principal in my account. After 2 years, how much would I have? I'll start you off and say, well, if we're giving them $110 or they're pretending that we've just given them $110, I'm definitely getting my $110 back. But then how much more am I going to get on top of that?
Wait, I'm sorry, would you ask that again?
Yeah, so the bank says we'll give you 10% interest on your investment. And now they're saying that your investment is $110 after 1 year. Now you have $110. Now they're kind of rolling it over as like as a new investment. It's as though you just gave me $110. So now how much am I going to get in interest?
110 times 0.1.
There you go. So that's like saying, okay, I'll get my original amount back plus 10% of that on top of it. And so now, and I'm just going to go ahead and do this calculation. That's 110 plus, why I did this one, because it's super easy to take a percentage of this, or 10% of something. I just moved the decimal place over once, and so I end up with $11. And now 110 plus 11 is $121. Okay. Now they say, hey, keep it in here for another year. Keep it in for a 3rd year. We'll give you another 10% on top of that right there. So how much would I have after 3 years? What do I need to write there to do that calculation?
121 plus 121 times 0.1.
There you go. And now we're kind of getting into the weeds. I don't really want to do this calc, although we can. That's not too hard. So 121 plus multiply by 0.1 is the same thing as divide by 10. Dividing by 10 takes my decimal place, moves it 1 place to the left. And so that's 12.1, which I don't want to screw this up. 12.1. Just going to add those together. It's 1.331 right there. 133.1. So if my original question was, you invest $100, the bank will give you 10% interest, compounded yearly. That's how they say that. Compounded means, that's what this is. We're compounding. We're saying, okay, every 1 year this rolls back over, and it's like we will start giving, we will take this, the interest that we gave you, and we'll put that in as our new calculation. So they say compounded yearly 10%. How much would you get after 3 years? You would say $133.1 you would have in your account. If they asked, you know, how much would you make? I guess that would be $33.1, and there's some subtleties to that. But this seems like a really bad way of calculating this. Maybe there's an easier way, and indeed there is. And this is the thing to notice. In this first case, we could have rewritten this like this. Say, well, hold on. 100 plus 100 times 0.1. Can I factor anything out of that expression? Is there a common factor in each one of these?
100.
100. So I could pull out a 100, and what's left on the inside here? Something plus something.
Would you ask that one more time?
Yeah, what I factor out 100, what do I get when I factor out 100? This equals what's left in here.
I don't know.
So how about 1? And then what if this? So let's take a hard problem and turn it into an easy problem. If I had 2 plus 2 x, and I factored out, do I have a common factor? What is it?
2.
2. And what would be left over on the inside?
1 plus x.
1 plus x. So it's almost exactly the same thing, only in this case our x is just some number. It happens to be 0.1. And instead of a 2 in each case, it's a 100. So I pull out the 100 on the outside, and I'm left with what and what?
1 plus 0.1.
1 plus 0.1 right there. And I'm going to write that as 1, 0 because I liked it. 10%, I want to see that as a 10. Like if I had 37%, I would see it as 0.37. That's just how I like to do it. So there's that right there. So now notice something here. This right here, this thing is equal to 110. We did that calculation, right? If I had taken this, thrown it back in, I would have 100. Throw it back in, I'd have 100 times 0.1, which is 10. And so this entire thing would come out to 100 plus 10, which is 110. And then what did I do in the second case? So what I'm saying here is I could have rewritten this as 100 times 1 plus 0.1, like that. Can I factor something out of the second equation? This thing right here, 110 plus 110 times 0.1. Is there a common factor that I can pull out?
110.
110. And what's left over on the inside?
1 plus 0.1.
1 plus 0.1. Okay, so let's look at that. So in other words, what I get after 2 years would have been the same thing as would have been the same thing as 110 times 1 plus 0.1. Right there. Okay, one last one, and then we're going to gasp and we're going to have some shock and awe here in a second. So we have in the third year, the way we found out how much money we're going to get was we did this calculation. And so, is there something we could factor out? If so, what is it and what's left over?
Uh, 121 plus 1.1 times 1
Yeah.
plus 1 point. No, whatever that number is.
Yeah, that one right there. Right? Okay, so now let's take a look at this. I'm going to rewrite that just below this right here. So we have 121 times 1 plus 0.10. Right there. That's how we calculated this. We started off by saying, well, 10% interest. Of course, it's going to give me back what I started with. And then it's going to give me an extra 10% on top of that. So one way of doing that is to actually take your original and then add that to the amount that the 10% of what you started with. Another way of thinking about that is, well, we could have just taken the original amount and multiplied it by this number 1 plus 0.10. And at this point, you're saying, Justin, why don't you just write that as 1.1? Because for the same reason that I'm using tens and hundreds is because we want to try to keep this as general as possible. These numbers are about to get uglier, and we don't want to oversimplify too soon. But watch this. We found, and we did this calculation, we said that this times this number right here is exactly the same thing as 110, right? Do you believe that? This times this is equal to 110.
Yeah.
Yeah, right. Because I mean, we did it explicitly, right? It's factored in. We said, okay, that's the same as 100 and that. And actually, we'll just make 100% sure here. 100 times 1 plus 0.1, just like that. It's 110. I could also have written, like I'm saying, times 1.1, 110, but it's going to be nice to keep our rate. That's what this is, the interest rate. It'll be nice to keep our rate separate like that for what we're about to do. So, okay, I take 100 and multiply it by 1 plus the rate, and it tells me what I get after 1 year. Then I take that number and multiply it again by this to find what it is after 2 years. In other words, it says take 110, the output amount from your first calculation, and do this right here. Now, this is where we're going to, this is where we have a big payoff here, is we just said that 110 can be written like that. To find the amount that we would get at the end of the second year, we said that we would take the first amount, 110, and multiply it again by this, 1 plus the rate. So that's what I'm saying right here. In order to find how much we'd have after year 2, we would take 110, the amount we invest, times 1 plus 0.1. But look at this. What did we just find that 110 was? Well, 110, how did we get it? We took 100 and multiplied by this. So instead of writing 110, I'm going to rewrite that as 100 times 1 plus 0.1. That's what that is, right? To be clear, I'm taking this number and just showing how I got it. And I'm just kind of expanding it out right there. Like you just said, 100 times 1 plus 0.1 is 110. And so then we take that and multiply it again by that factor right there. This is the same thing as that times that. Let's take a look here. That's 100 times 1 plus 0.1 quantity squared. Okay. So let's see. In fact, I'm going to go ahead and write that right here. I'm going to say this thing right there, which we know is we could calculate this too, right? We could take 110, multiply it by 1, you get 110. Multiply it by 0.10, you get 11. 110 plus 11 is 121. This is 121, but we found that it's the same thing as 100 times 1 plus 0.1 quantity squared. Let's check that. Go to my calculator. Okay, we said that 110 times 1 plus 0.1 should be 121. Yes, it is. We said another way of doing that is we could have just taken my original amount, multiplied that by, take my original amount, multiply that by 1 plus 0.1. And now we're saying, well, it's been 2 years. So this was compounded twice. So this is the same thing as just taking that number and squaring it. Look at that. We do get indeed 121. So one last step here is to say, well, wait a second. The third year, how did I get this? Well, I took 121, but we just said that 121 can be calculated in a pretty simple way here. So we take the amount that was left over from year 2 and multiply it again by this number, which is the same thing as saying you get your original amount back, you get your 121, and then you get an additional 10% on it. That means the exact same thing as that, which does work out to be 133.1, blah, 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 blah. But there's an even easier way of thinking about it is saying, well, wait a second, 121, the way that we got this 121 right here was by doing this calculation. By saying, well, 121 is the same thing as 100 times 1 plus 0.1 squared. And that's what I've done. I've just expanded this 121 to show how did I get it? Where did it come from? It didn't just fall out of the sky. It came from doing these calculations. And then we multiply again by the exact same number, which we could say is 100 times 1 plus the rate as a decimal to the third power. And that's kind of nice that after the first year, you take 100 and raise it to the first power. You got 100, you're 1 plus the rate, raise it to the first power, and you get how much you have after 1 year. After 2 years, you simply take your original amount, take 1 plus the rate, square it for 2 years, and you get the amount you'd have after 2 years. For 3 years, you simply take your initial amount, multiply it by 1 plus the rate cubed for a total of 3 years. And so this is just begging to be generalized here. There is nothing special about using $100. I could have said $50. I could have said $742.33. And we would have ended up doing all of this stuff and factoring things out. And whatever that initial amount I had would have ended up right there. And so that, I want to get rid of something. I'm going to get rid of this middle stuff. Can I get rid of this middle stuff right here?
Yeah.
Okay. Is this making sense? Like how I finally arrived at this bit right here?
Yeah.
Okay, good. So what we've done here is we found, and I'm willing to bet that if we kept doing this, if we just kept doing this and we went down, 1, 2, 3, 4, 5, 6, all we're going to do is take the old amount, and so let's do that for just real quick for P4. How much would I have the next year? Well, I would take whatever amount I had in the previous year, which happened to be 100 times 1 plus 0.1 cubed. I would take that and multiply it by, lo and behold, the same amount, 1 plus the rate. Why is that? Well, you take your 133 point blah, 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 and you multiply it in, and it gives you back that amount that you had. It also takes 10% of, right? That's what happens when you take a number and multiply it by 0.10. It takes 10% of it, and then you add them together and you find the total amount that the bank's going to give you. And so we could think about it that way, or we could simplify things and say, oh yeah, it would be your original amount, but now this is the same bit, 1 plus 0.1, 1 plus 0.1, that's a total of 1 plus 0.1 to the 4th. And now I could just generalize and say, yeah, and when it's the 5th year, you would have to the 5th. When it's the 6th year, you would have to the 6th. When it's the nth year, you would have had this, a total of n times. The 1 plus, and I'm going to call it 0.10 like that, n times. And so let's see if we can generalize this. So this was my original amount right here. That's what we're going to call P0. It's my initial amount. So just to be clear, P0 is my initial amount. Of course, you're going to get that amount back. So you have a 1 there. You're always going to have a 1 there. And then what's going to be added on is your interest rate. And I'm going to call that a lowercase r. Interest rate. And it's a percent. Meaning it's some number between 0 and 1. Unless some place is offering you over 100% interest, in which case you should throw all of your money into there because that's ridiculous, but that's never going to happen. Also, you know, or in the context of interest that you're going to owe, say on a car, then that thing had better not be a 1, because if you're paying 100% interest on your car, that's not good. And so then the interest after, or I'm sorry, then the principal after n years, if this is compounded every year, is that right? The initial amount, P0, times 1 plus your interest rate as a decimal percent, raised to the power of, well, the number of years that you've invested or whatever. And so here we go. Here is an example of how we're going to use this thing right here. I'm sorry, give me just a second. And then trying to get done here as soon as we can. Now, the way it is in your book is they use it instead of the n, they use it as a t for time, right? So that P0 1 plus r to the t, which is nice. And in fact, when we go to talk about this on Monday, we're going to go into compound interest, which is much more difficult. But in this homework, this only makes sense in context of full years, right? Because this is kind of how banks work. If you don't have it in for the full year, then it's like it never happened. You have to have your money in the account for the full year in order to get this. And so I like to use an n to make us think about that, like that it's an integer value, like it had better be a whole number. We will be talking about not whole numbers soon, but this is show you how this works. So yes, okay, you really only have one of these and it will do that. Okay, so here we go. Finally, I'm going to leave this on the board so that I can do this. This is number 26. how many years will it take an investment of $1,000 to double itself? When the interest is compounded annually. The two ends and annually. Who cares? At 6%. So this is the full question in the book. Now remember, the compounded thing is compounded means that we're taking the amount that you have and putting it back in and recalculating, right? Just like when we had the 110 plus 10% gives you, or 100 plus 10% of that gives you 110. Then we took that value and put it back in, and that's where this nifty formula came from right here. So we had the initial amount, and we're doing that over and over again, and every time we do that, it goes there. Compounded annually, we're talking about that's the number of years then. And so just thinking about this, how long will it take an investment to double itself? So first off, I'm going to identify a few things. The initial amount, P0, the $1,000. So there's my P0. The 6% is the interest rate. And so that means R equals what in terms of a decimal?
Okay, hold on.
Okay.
Mm-hmm. 0.6, right?
There you go. Now I'm going to put a 0 out front just so it looks sweet. So yes, 0.06. And if you're ever worried, right, you say 6%. Oh, wait, there's that. And we're going to move it literally 2 places to the left, putting it here. Okay, I pick up a 0. Yeah, 6%. So that's 6%. Okay. Now, if you think about this, right, like we could just do this calculation and just say 100. Okay, we'll get 1,000 back plus, and then we take 6 times 0.6 times 1,000. We get that, then we add it together and ask, did it double itself yet? No. Okay, we'll do it again, and we could do it again and again and again, or we could use this nifty fact right here. And so we have almost everything we need, right? It's asking, how many years will it take? So in other words, solve for n is what they're saying. They want to know what number n should we have. So that's nice. How many years right here means solve for n. Now the only thing we're missing, because now I'm looking at this and I'm thinking, okay, I have my initial amount P0, good. I have, well, 1 is always 1. Don't need to worry about that. Plus R, I have that, that's 0.06. Got it. N is the thing that I'm looking for. Okay, I'm good to go. Uh-oh. Wait, I don't know what this is supposed to be. But it says, how long will it take to double itself? And so to double, if the investment doubled itself, what should that be? What is, what, you tell me. What should the output be if something has doubled itself?
2,000?
It should be 2,000, right? So that means, okay, the number, the output number, the return on the investment doubles itself means, yes, it should come out to 2,000. Okay. And so, okay, I think we have everything we need to know here. So I'm going to say, all right, the PN we know is 2,000. The P0 is 1,000. 1 plus 0.06, so I'm going to go 0.06 raised to the power of n. And now we're solving for n. N is locked up in an exponent. So I'm going to say, okay, there's this. We did almost exactly the same thing earlier, right? We have some number equals some number times some number raised to some power. No, I could do that, right? We just start undoing that. And I'm going to say, okay, let's get that 1,000 out of there. The same way we did earlier. Divide both sides by 1,000. And that gives me this guy. What's 2,000 divided by 1,000?
Two.
Yep. All right. Okay, how do I get that n out of the exponent?
Would you use the natural log?
And again, you could use any log you want, but I think natural log would be the best. We could use log base 1.06. Good luck finding a log base 1.06 key on anything. And so, yes, we're going to use natural log on both sides. Natural log of 2 equals natural log of 1 plus 0.06. And okay, now what do we do?
Okay, so now you can take the n out, right?
Exactly. That's the whole reason we did log in the first place, because it has that nifty property. Our favorite property of logs is it makes exponents drop out. We, up until this point, have not known how to make exponents come out of something. Well, now we do. So we have natural log 2 there. Okay. I'm going to go ahead and, well, yeah. Since we have an exact number here, right? 1 plus some number, I'm going to go ahead and write it as whatever 1 plus 0.06 is, happens to be 1.06. Just to make life a little bit easier, I'm going to go ahead and do that right now. I'm going to say, okay, that's the same thing as 1.06 right there. Could have done that at the very beginning, just whatever. This is where I'm doing it. Okay, now we're trying to get n by itself. In other words, we're trying to solve for n. So what do we do to this?
Would you divide by the natural log of 1.06?
There you go. That will get your n all by itself. And so on the left-hand side, we're left with natural log 2 over natural log 1.06. And that is something I could plug into a calculator. Which is what I'm going to do right now, because there's more to this problem. Oops. There's subtly more to this problem. Okay. I'm going to share this. So we have natural log of 2 end parentheses divided by natural log of 1.06 end parentheses. I hit enter and okay, 11.896. Oops. So I'm going to write that as approximately equal to 11.896. 0.896. Just like that. Okay, now got to stop and use our thinking caps here, because the way this works, we can't say, because of the way that that compound interest works, the bank's not going to give it to you until you've gone that long. And so we can see 11 years is too short. It won't actually reach this value until 11.89 years, but banks are jerks and they want to hold on to your money. So it's not going to roll over in, I don't know, 0.89, like on November 14th or whatever that is, right? Like 11 years and then another 0.89. So sometime in December, I guess. It's not gonna, they're not gonna say, oh, it's December, you just go ahead and take it. It's, you get your W. No, they're gonna hold on to your money until the last minute. So the actual years, and like I said, the reason I'm using N here is so that we're thinking about integers. What integer value should I answer for this?
Would you just do like $12?
There you go. We're gonna round up. Because again, the bank is not going to be nice and say, well, it's been in here long enough. It's technically, you've had it in until November. And so technically you've crossed the line. That is, if you plug in 11.896 into this, you'll get your $2,000. So you'll have, no, they're going to hold on to it till the end of the year and say, by the end of the year, then you can have it. And so we're going to round up. And that's the key with these guys here. Next time we talk, we're going to talk about, well, what if you don't? What if you want to take your money out? Is there more to the story? And there is. So kind of two ways we could answer this. We could, like, this is perfectly fine. You could say after N is this, but we know from the context of the problem, they're saying how many years. They're not saying how much time. They're saying that this is a total number of years. This is an integer value of years. And so in this context, the bank's not going to be cool. They're going to hold on to it till the end of the year, which would be a total of 12 years that they've had your money. Real quick, I want to do one thing before we're done. Same question. So you got this? This makes sense how we did all this?
Yep.
I think you only have one question like this, and it's almost exactly the same question. Here's something interesting. Let's say that this exact same problem were given, and they said, how many years will it take an investment to double itself when interest is compounded annually at 6%? And you go, well, it depends on how much money we started off with. Or does it? Because let's think about this. How much will it take an investment? We don't know how much we started off with, but it could have been any investment. Like it could have been $100, it could have been $1,000 or whatever. Let's just call that initial amount. Let's just call it P0 is the initial amount that we have. Well, then if it were 100, let's do it this way. If it were $100, how much would the output be for double itself? What's double 100?
200.
What's double 1,000?
3,000.
What's double 521? Don't do the calculation. Don't give me the final answer. What are you doing in your head? 521 what?
Times 2?
Times 2. That's what you're doing every time, right? If it's like, if something's doubling itself, you're just taking whatever that amount is and you're timesing 2, right? So if it's 100, you times 2 and get 200. If it's 571, you take 571 times 2 and get, well, whatever you get. So if it's P0, What's double P0?
0 times 2.
P0 times 2. So we'd say, well, wait a minute. Okay, it was an investment. We don't know how much it is, but I can tell you that if it doubles itself, that it's 2 times whatever it was originally. And so we'd go, okay, all right. So now we're going to plug it into here and say, okay, the original value was P0, 1 plus 0.06 to the n. And the final value, the amount that we're going to be getting out, is double P0, or 2 times P0. And then you go, oh, I don't know how to solve this. I have so many variables. And I say, well, no, because look, solve for n, right? Solve for n. And so don't use your brain. We're just going to say, okay, this is the thing I'm trying to get by itself. And we're going to take exactly the same steps as last time. Say, this thing gets thrown up into an exponent, okay? And then he gets multiplied by P0. So how do we undo multiply by P0?
Divide by P0.
Divide by P0. And look at that. That guy cancels out and we get a big fat 2, which is exactly what we got last time. Right? Because last time we had 2,000 divided by 1,000. It turned out to be 2. This time we just get 2. And so this is something you might see in the future. I'm not trying to be tricky here, or like, give you a wink and a nod. I'm just saying, like, these types of questions show up all the time. How long will it take an investment to double itself? Boom, right there. Like, you don't need to have an exact value of whatever the initial thing was, because guess what? It's going to cancel itself out anyway. If my initial value was $9,000, I would have said, oh, 9,000 times 2 is 18,000. And then guess what? I would have divided by it and got back to 2. So have I made my point?
Yes.
Yeah, cool. Okay, so homework is actually, you got lucky. You got lucky because I'm long-winded and we didn't get to everything we get to do. So I'm gonna get rid of this. And it's pretty much, I think I've given you an example of every type of question that's going to be on this homework. So homework, it is chapter 12 again, section 7. I believe this is still 7. Yep. And this is going to be from pages 547, 547 through 548. We're going to do numbers 27 through 37, odd and the stuff from last time that you didn't turn in. So the let's be clear about that. So I want to make sure you did 41, you did 39. So 43 through 51. And this is from last time.